Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the Module 5 Inquiry 3 question. This is going to be looking into things related to Kepler's law. The 2020 HSC Physics paper, question 31. We have the orbit of comet P. The question here says account for the changes in velocity of the comet as it completes one orbit from position P. So it could be moving around here and then back like so. So what we want to look at is what's the velocity here, and we could even look at what the velocity of position P would be here. What we can expect is as P is in this position here, the gravitational force exerted by the sun is quite high. So the gravitational force from sun is quite high in comparison to the gravitational force here, which has a significant decrease. Okay, so that's kind of one of the things we can look at here. You can also look at this in terms of conservation of energy. So on this position here, P, its gravitational potential energy is quite high. If you recall, gravitational potential energy is expressed as the following formula: GMR negative. Okay. We also know that gravitational force is expressed in the following formula: squared. Okay, so if we actually have a look, in this position XP here, the radius is quite far, or R at position X here is much bigger than this position here. So we can expect that the gravitational potential energy is much bigger or more negative on this position than this position here, which means that we will have a very low kinetic energy. And as we know, kinetic energy is directly related to velocity. Okay, so we can expect that the velocity would also be quite low here in comparison to this position here. You could also explain this in terms of the gravitational force. If the gravitational force is a lot stronger here, that means that the acceleration on the comet P would be much faster in this position that I'm highlighting here in comparison to this position on the left here. So that's a couple of ways you can explain it. Let's just try and write it out here. So in comparison to velocity, so comparing velocity, so position P, velocity is low, okay, relative to position, and I'll just call this position Q. Position Q. Q is at a high velocity at. Okay, now the word account is equivalent to saying explain. So we want to explain why Q at position Q here it is high and why at position P it's low. I'll change color. Okay, come down here. Okay, so the reason being is at position P, so the distance between comet and sun is at maximum. As a consequence, hence, gravitational potential energy is high and kinetic energy is low. Okay? As our comet is moving closer towards the sun, it's losing gravitational potential energy and it's gaining kinetic energy. And as a consequence of gaining kinetic energy, it is going to move a lot faster. Its velocity is going to increase the closer it gets towards the sun. So it's low. So as a comet moves closer to the sun, kinetic energy goes up and gravitational potential energy goes down. This is obeying the law of conservation of energy. Hence, an increase in velocity of our comet as it comes near the sun in its orbit. Okay, you might want to also add, if you had space, that also results as the comet moves away from the sun, it's losing gravitational potential or it's gaining gravitational potential. So as it goes this way, we're gaining gravitational potential and losing kinetic energy. As we rotate towards this direction, we are losing gravitational potential and gaining kinetic energy. So that's one or two ways you can go about that question. Okay, question B. It says we have two stars, A and B, of equal mass, separated by a distance x, interact gravitationally such that the speed of A is constant. Derive an expression for the speed of B. So we are looking at, from the looks of it, orbital speed based on the gravitational attraction of the two masses. So let's get into that. So previously we stated, so we're saying the mass of A and mass of B is the same. Okay. So we previously stated the formula for gravitational force in the universe is G(m)(m)r². Now we know that the distance r is, or x will be equal to r. We know that the two masses are equal to each other. Okay, so we can just re-express our equation to appear like this: m² equals to x². Okay, that's the first step. Okay, next bit I'm going to do is just going to draw a little diagram. We have the mass A orbit, and then we have our star B orbit here. They are being separated by a distance of x. They both exert a gravitational force onto each other. Okay. And as we know, if they both exert a gravitational force onto each other, okay, it means they are going to interact, they're going to pull each other, they're going to orbit around each other. Now, if A is moving at a constant velocity, you know it's not a direct being pulled in towards B, right? The part of A here, if it's moving at a constant velocity and it's being pulled by gravity, you can expect it's going in a circular orbit. Okay, so it's a circular orbit that we're seeing here. Now, if we're seeing a circular orbit, we should also expect that there is centripetal force involved. And we know that centripetal force is mv² r. In this case, this r here is the radius of orbit. So radius of orbit. This r here is the distance of separation. So they're measuring two different things. So just make sure you don't get those two concepts confused here. We said that r² or x² represents the distance separation between these two, and x is actually measured to the center point here. Just to not confuse ourselves, I'm going to change color. Okay, next part is working out the direction of orbit. If they're both at the same mass, so we said that both of them have the same mass, that means that their, their orbit is not going to be favored on either side. So A is not going to be orbiting closer to B. B is not going to orbit closer to A. They're going to just sort of meet halfway in their orbits. Okay, so they're going to be, A is going to be pulled equal amount of B. So if they're going to be met halfway, and we know that the distance that they're separated by is x, then their radius of orbit would be x divided by 2. Okay? Because if both masses contribute the same amount of force, or the, not same amount of force, sorry, if both planets have the same mass, their center in this orbit will be directly half of each other. Something like that in a picture. Okay, so our center of orbit is somewhere along the lines where they kind of rotate around each other like that. So if I substitute x divided by 2 into r here, I'll get rid of this component. It'll look something like this. This is what our equation will end up looking like. x2. If I change it around, it'd be x squared equals to 2mv squared over x. Okay? Easy done. We want to find the speed on B. Here's our velocity component. Okay, we already know what the velocity of A is. It's constant. We want to know what B is, or how to find an expression for B. So move the equations along. X will be times up here. So it'll become gm squared times x, 2m down here. So it'll be 2m times x squared. That equals to v squared. Okay? Just put it down a little bit more. Change color again. So this x is going to be cancelled out. This x will become just x. This m cancels out. We get m here. Okay, so it's big G m divided by 2x. Root that by v. So the velocity of our B orbit here is equal to the square root of G m2 times x. And that's how you do this question here. Alright, so certainly this one is quite a challenging one, because you also have to look at different aspects of the gravitational force and centripetal force. There are some minor hints given to you here and there, so you really need to read the question really carefully. Deriving equations do seem to come up quite a bit in the recent news HSC syllabus, so do more practice questions on these kind of things, and hopefully you'll get a better appreciation of how to do these equations for future exam type stuff. If you enjoyed the video, please give this a like and support future publications of other videos. Thank you.